So let's get started. Well, yeah. Okay, so the first announcement. Can you hear me? Hello. Mic working? Hello. Hello. Yeah. So the first thing is I made an announcement. I'm sure you guys have seen it last night. I extended the deadline for Feifei for 5 hours. That's really to encourage you to come to today's lecture, right? So instead of 5 p.m., it will be due tonight at 10 p.m. And the way you submit Feifei is you will do the same thing as you have done in phase 2. Basically, you public underscore HTML folder and submit that zip file through Hanyin. And in addition to that, you want to make sure all your source code are placed into the public underscore HTML folder on Georgia server under your account. Okay? So this is important because TA will grade you phase 3 based on whatever that's there on your Georgia account. Okay? So you want to make sure you fully test your code on Georgia server. I hope you understand this because we are not able to reproduce potentially 140 different local environments. If you do your development locally and you have some dependency that we are not aware of, we are not able to reproduce that in the grading process, right? So we have to use the same setup, that's Georgia server, to grade your submissions.
Yes, specifically the path, relative path, use local, your path may be different.
Well, you know, there are many specifics we can do on this. We can take this offline discussion. But the bottom line is you want to make sure you upload your code to Georgia and test yourself and make sure it's working over there. If it doesn't work there, contact one of the TAs or me before the deadline. But don't get panicked. If your code for some reason works on your local environment and after uploading to Georgia it doesn't work, during the grading process we will contact you if that's the case and see if that's something easy to fix. If it's some simple library dependency problem, of course, in that case we will fix that. But if it's more than simple library dependency, there's some bug in your code, then obviously you will take a ding in your credit, right? But if it's some simple library dependency stuff, try to fix it before deadline. Of course, if you didn't get a chance to do that before deadline, you do everything locally, you upload and suddenly things doesn't work, then don't be panicked. Okay, contact us during the grading process. Okay, does that make sense? Any other question you have regarding phase 3? Now, I made a few comments on phase 2. I think it's really common sense, but some of you contact us, right? Like, I work this many hours, do I deserve some more credits? I'll give you a simple argument. You buy a car, okay, from one of the dealers, let's say Ford or Toyota, whatever, right? You go back home, the dealer promised you this car has 100 functionalities. So you pay whatever, let's say 30 grand for those 100 functionality. And 2 days later, you realize 80% of the functionality do not work. You come back to the dealer, and dealer said, you know what, we spent 10 years building this car. So we deserve the money you give us. Would you buy the argument? Probably not. You probably will say, I don't care how many hours you put in building that car. I paid the money for that 100 functionality. You better deliver those 100 functionalities. Whether your car is built in a day, or 2 days, or 10 years is irrelevant. Same argument here. Does it make sense? I appreciate the hard work you put in, don't get me wrong. But unfortunately, hours and how much effort you put into the product, when it comes to the grading part, irrelevant. Okay? So I want to get that clear. And some of you also said, oh, I submitted the wrong files, or I didn't manage to submit properly, or whatever. I understand things can go wrong, but remember, Hanyin is a tool that allows you to actually check what you have submitted. Okay? That's probably part of my fault. I should have made it clear in the product specification. Hanyin actually allow you to see what's submitted. But I assume that you guys have used Hanyin before and blah, blah, blah. Anyway, if that case applies to you, contact me and come to my office. And I will check with you. Of course, you have to show strong evidence that you have done those before phase 2 deadline. Timestamp alone, sometimes I cannot buy the argument alone because if it's on your local computer, you can easily force the timestamp on the file. I'm not saying you will do that, but what I'm saying is I need to take a closer look. I cannot just take your submission as it is. Does that make sense? To be fair to the rest of the class, if we have 140 submissions, only less than 10 such cases arrived. Most of you did okay. Okay? So, so if those cases apply to you, come to my office. Don't be panicked either, right? That doesn't mean I will not allow submissions now. If you made a mistake in your phase 2 submission using Hanying, something went wrong and your file was not properly submitted. All I'm saying is a case-by-case investigation that I have to take. Don't assume by default I will take whatever you gonna give me and use that for regrading, right? Because if that's the case, every one of you can come back to us. I didn't submit this properly. Can you do this? Then everybody got happy in the end of it. What's the point? Okay. So, but if this applies to you, don't be panicked either. Like I said, I will take a closer look and resolve these issues on a case-by-case basis. Okay. Any other concerns, comments before we move on to today's lecture? Not. Yes.
I had a question.
Yeah, go ahead.
So if we submit our source code, like a zipped up folder, and then we end up finding a bug, just testing our web page, and we change it a little, do you want us to resubmit the webhand in?
Before as long as it is before the deadline, yes, we submit through Hanying. But like I mentioned in the announcement, make sure you stop editing any files on Georgia server after 10 p.m. Because anything you do there may invalidate, not the entire submission, but invalidate any files that have a timestamp after 10 p.m. tonight. Those files will be removed from the grading of your case. Brandon.
Why are we doing the webhand and if it's already on Georgia?
Well, good question. The reason is we want to make sure we have a copy of your code, because as far as I can tell, you have no way of forwarding timestamp on Georgia. But I want to just make sure, there are some ways that I'm not aware of that you can somehow manage to change the timestamp on Georgia. So does that make sense?
Yeah.
So I want to kind of have a proof of your files before that. Yes.
How much focus should we give for error checking?
Well, like this goes to your phase 2 as well. No, you don't have to. We are not playing the adversary role, right? So as long as you follow the spec, you deliver the functionality on typical standard input. That's fine. You don't have to worry about things like security VIN number must be 9 digits. Of course, we appreciate if you do that, but the purpose of this product is not on those particulars. Does that make sense? So use common sense. Okay. Any more questions? No, okay, fantastic. All right, so last lecture we talked about these structures and disk space manager and buffer manager. Now we have a good understanding of how database system works. You have your data, which is record from your table, that sits somewhere on disk. Then you have this buffer manager and disk space manager working together to fetch data from disk to your main level buffer so that the higher level applications can operate on those data, either read or write. And we also know that the unit of any such operations is page, one page at a time, either read or write. So whenever you need a page of data, you go and talk to the buffer manager. If it's already in the buffer manager will return you the frame number that hosts this particular page, and then you can look at the content of that page. In that particular scenario, you don't have to pay a visit to the disk in order to get that page of data. On the other hand, if this page of data is not in the buffer manager will then talk to the disk space manager, and disk space manager will go and fetch this page somewhere on disk and bring in that into the buffer. And the way to do that is you pay a rotation delay, sync delay, then rotation delay, then you convert that one page of data to to one page of data in main memory. And you can do that sequentially from multiple pages. That typically is much more effective than doing the same number of pages but using random IOs. Those are the discussions we have. And that's pretty much what's covered in your homework 3, problem 2 and 3. Okay? Now today we're going to talk about give you a little bit more details as how data are organized in disk. So far, this is kind of like an abstraction. We have table of records that go to disk. They are stored as some pages. But how these pages are connected together, we don't know yet. Furthermore, we see there's a big difference between sequential I/O and random IOs. Okay? When you try to read data from disk. And there is a big difference between what buffer replacement policy you are using, IRU or MRU, and depending on your request sequence. So all this tells us we as a DBMS, database management system, need to be smart about the order of retrieving pages and the manner you retrieve those pages. And, at the end of the day, even if you're reading the same set of pages, the way you retrieve them and the way you store them on disk could make a huge, huge difference. For example, I'm reading 100 pages. These 100 pages are sequentially stored on disk versus I'm reading the same 100 pages that are randomly stored on disk. Big difference in terms of running time. So how does a DBMS address those issues? So today we're going to give you a quick overview of this. Of course, keep in mind, we're not able to dive into the full details because we only have one lecture left, and this is the undergraduate class. But I do like to give you kind of like an overview so that you are aware of this if you become a database administrator for some companies one day. So that you are aware of these issues, you can optimize the performance of your database system at least. Okay? So, file of records. So in a DBMS, records from a table are organized into what we call a file, a database file. And a file is nothing else but a collection of pages, a collection of these pages. And each page is nothing else but a collection of database records. So that's kind of like the breakdown, right? So you have a table of data, like students, that have many, many records, right? So this student table will be stored in a single file. And this file may have multiple pages, and within each page you have multiple records. Let's say each page may have 100 student records. If you have 100,000 records, then that's translated to 100,000 over 100 pages divided by 100. That's how many pages you need to store those many records because you have 100 records per page. Okay. So that's kind of the high-level overview of what to expect. And a file is a collection of pages, each containing a collection of records, and must support the following operations: insert, delete, and modify of records, obviously, right? So I want to update a particular student record value. That needs to be translated into update a page containing that particular record on disk. And this update operation may refer to insertion, deletion, or modify some existing values. So that's what the first functionality you need to support at the database file. And the file also needs to be able to fetch a particular record. And this is typically done using something called record ID. Record ID is a unique identifier for each record in your table. So every student has a unique record ID. And this is different from, by the way, the primary key of your table. This is different from the primary key of your table. So primary key has semantic meaning. For example, social security number of student record. That has a semantic meaning. Record ID is solely for the purpose of figuring out the location of this record on disk. So it's kind of like a pointer or handle to the record on disk. That's the purpose of record ID. So this is different from the primary key of a record. Of course, record ID must be unique as well because every single record will be at different locations on disk. So record ID values must be different for different records. And then not only we need to be able to fetch a particular record, we need to be able to support the linear scan of all records. I want to print out all student records. So of course, you can argue if you can do function number 2, you should be able to do function number 3, which is fetch record 1 by 1, right? If you know all the record ID values, then you should be able to just call function 2 multiple times to accomplish function number 3. But the question is, can you do better when your goal is to simply scan all records? Does that make sense? Because, for example, I want to talk to each one of you. I can do this way. I can talk to each of you like this. Or I can talk to you, talk to you, talk to you, talk to you, talk to you. At the end of the day, I'll talk to everyone. Does that make sense? Obviously, there is a difference. This way is probably more efficient because I need to work less number of distances in this lecture room when I do that, compared to like this. So if you know your goal is to fetch all records, there's some optimization you potentially can do. Okay, so that's kind of the argument. So the default file structure used by the DBMS to organize records from different tables is what we call unordered heap file. So this name, actually, I don't like this particular name, but this naming convention already exists, so nothing I can do about it. The reason I don't like about this naming convention is heap file. If you look at the concept of heap, in main memory data structure, heap is actually a sorted data structure. Everything in a heap is sorted. Does that make sense? Actually, if you look at STL library, standard template library implementation of heap is implemented by a binary tree. So records or items in a heap is sorted. Does that make sense? But in the context of disk space manager in a DBMS, a heap file referred to unordered or unsorted file. Meaning records in a page are not sorted, and records across pages are not sorted either. There are no particular sorting order whatsoever in a heap file. Does that make sense? So this is somewhat counterintuitive if you know the concept of heap from main memory data structure. But if you don't know the concept of heap from main memory data structure, then that's fine. There's no confusion. Okay? But just keep in mind this subtle difference when you talk about heap in main memory data structure and talk about heap file in a database management system. One is sorted, the other is not. And the heap files support these operations, which is to keep track of the pages in the file, keep track of free space on pages, and keep track of records on a page. These are some basic operations you need to support. And there are many alternatives to achieve these functionalities. We will consider 2 alternatives in today's lecture. Okay. This is alternative number 1, heap file implemented as a list. The way you understand this is as follows. So you have, for each heap file, typically in a DBMS, every single table goes to a single heap file. So student table will have a student heap file on disk. Enroll table will have an enroll heap file on disk, so on and so forth. Okay? Imagine this is one particular heap file. The structure of it is that you're going to have a header page, denoted as that red color page over there. And you have 2 double linked lists of pages, 2 double linked lists of these pages. The top list, denoted by gray color, is a linked list for data pages that are full of records. So each page contains a set of records, and they are full, meaning no more space for any more record into that page. Remember, a page has its capacity, right? Typically, a page is 4 kilobytes or 8 kilobytes. And records occupy some number of bytes as well, depending on the schema of your record, right? So let's say each page is 4 kilobytes, and each record is about, let's say, 100 bytes. Then you can store about 40 records per page, roughly. Does that make sense? So the pages on the top list means those pages, each in that particular setup, has roughly 40 records already, and there's no more space for any more record going to any of those pages. So I store them as a linked list on top. What about the list down below? Well, quite on the contrary, those are the pages that still have free space for more records going to those pages. Does that make sense? What about the header page? Well, the header page stores some kind of metadata information about this heap file, like the name of the file, which table it is responsible for example, student table. Does that make sense? The pointer to the starting address of the top list and the starting address for the bottom list, and so on and so forth. So the header page stores metadata information as such. Okay? Now, and every single page in a database management system has a unique identifier that's managed by the disk space manager. And that's what we call the page ID. So you can think about each of these pointers as the page ID value of the page. So it's not really a pointer, but simply the page ID value of the corresponding page. But once you know the page ID value, it's kind of like you have a pointer to that page. The disk space manager will be able to translate that page ID value into a disk space address and go and fetch that page for you. Does that make sense? So there is this translation mechanism implemented by the disk space manager. Now take a page ID value and translate it to a disk location. The header page ID value, meaning a pointer, imagine a pointer to this page, that page ID value is stored somewhere called the metadata for your database. Every single database must have a metadata table, and that metadata table stores things like this: the page ID value of the header page of your heap file. Why this is necessary? Because this allows the DBMS to go to one location, which is the metadata table, to find out the starting address of a heap file for any particular table. And then from there, I can go and fetch any record from that particular heap file. Does that make sense? So that's kind of the setup. So what's the benefit and the disadvantage of this particular approach? One benefit is clear. The overhead of this approach is minimal. Overhead in terms of storage. Okay? The only additional page you have introduced is the header page itself. All the other pages, you need them anyway, because in order to store that many records, you need that many pages. There's no get around of that. So there's no overhead in those two lists. The only overhead you have is that header page. Does that make sense? However, fetching a particular page can be expensive because you have to trace down this linked list kind of structure. Does that make sense? That's kind of like the inherent property of a linked list data structure, right? So fetching a particular page can be expensive. Okay. So what's the alternative structure? Here is another particular structure. So the idea is, okay, to address that limitation we just mentioned, which is fetching a page near you to trace down the linked list, I will get rid of the linked list. I don't use a linked list. Rather, my pages in a heap file can be anywhere on disk. I don't care where they are. But somehow I need to enable random access to all these pages. Right? I need to figure out where they are and remember that information. So the way you do that is to introduce what we call a metadata directory for each page. So every single page will produce a directory entry for you. The directory entry is a small rectangular box in the web page. So remember, each web page now has multiple smaller rectangular boxes. And each box denotes the metadata entry for a particular page. And this metadata entry will contain information such as, mostly, page ID of that page. Page ID, remember, like I told you, is kind of like a pointer. I tell you where this page is at on disk. And things like how many records are on that page, how many free space I still have on that page, and so on and so forth. So those are the metadata entry per page. If you have n pages, let's say n equals 100. If you have 100 pages, you're going to have 100 metadata entries. Does that make sense? So what you do in this case is you organize those 100 data entries into header pages, not just a single header page, potentially you may need multiple header pages. How many header pages you need? Well, depending on how many header entries you have, one per data page, right? And the size of each metadata entry that you have. And those two will tell you how many header pages you will need, of course, and also the page size. And that will tell you how many header pages you will need. But one observation, clearly, if you have n data pages, you will have n metadata entries. Does that make sense? However, this n metadata entries will be stored in X number of header pages. One thing that's clear, X obviously will be much, much less than the value of n, obviously. Right? Because each header entry, the metadata entry, is much smaller in size than the page itself. You need n pages for the data record, doesn't mean you need n pages for n metadata entries. Right? So that's clear. And so that's the structure. So what's the benefit of this approach? Well, the benefit is clear. In order to look up a particular page, what do? You need to do a linear scan of the header pages to find the header data metadata entry for that page. But then you only need to do you only need to pay 1 IO to load that page. You no longer need to do that expensive linear scan through the data pages. You're doing linear scan over the header pages. But the header pages, the number of header pages, which is the value X, is much, much smaller than the value n. So instead of traversing a list of roughly n pages, you are traversing X pages that's much smaller in size, so which means much more efficient. And once you find the metadata entry for the page you want, you do one random IO, one jump, to load the page. Does that make sense? So fetching data and updating, those are more efficient here. Of course, what's the downside? The downside is your overhead is higher in terms of how many header pages you need to maintain. In alternative one we just talked about, you only have one header page, no matter how big your file is. Does that make sense? No matter whether your file has 100 pages or million pages or a billion pages, you have only one header page. Here, the number of header pages will grow as the number of data pages you have in the file grows. However, at a much slower pace. At a much slower pace. Does it make sense? So that's the trade-off between the two approaches. Yeah.
It seems like you could organize your header pages in such a way that the space taken by each entry in that header directory is so minimal that the impact is almost.
Typically people will go with this because yes, I will have more header pages in terms of, so my storage overhead is bigger. But typically your metadata entry is so small in size, and you can pack so many metadata entries into one page, this overhead is not that significant. However, as n continues to grow, from a theoretical point of view, the overhead of alternative one is constant, which is just 1, regardless of the value of n. The overhead here is linear to the n. So theoretically speaking, does that make sense? So from a theoretical point of view, the overhead here is much bigger than the first one in terms of storage. But in terms of fetching your data and all that stuff, typically this is better. Okay. So that's about two different organizations of pages, data pages on disk. In addition to this discussion, I also have slides which I'm going to skip, by the way. How attributes in a record are organized. So remember, heap file tells you how you organize pages in a file. Right? You have multiple pages and how you organize into a file. But in addition to that, we also need to know inside each page, what do we have? We have a collection of records, right? How do you organize those records in a page? We haven't talked about that yet. And inside each record, we have multiple attribute values. how do we organize those attribute values in a record? Does that make sense? Those are two questions we have answered, which I will skip. We just don't have time to cover this. If you're interested, you can look at the slides, but I don't require you to understand this. I'll give you a quick overview. This is how you organize attribute value in a record, depending on whether you have fixed length attribute values or variable length attribute values. And then we talk about how you organize record in a page, again, depending on whether you have fixed length record or variable length record. One thing, the only thing I require you to remember is, suppose this is a data page, right? Of course, you have multiple such pages organized into a heap file using one of the alternatives we talked about, right? Inside each page, what do you have? You have records, right? So I just ask you to understand this abstract view that you have record 1, record 2, and so on and so forth. Does that make sense? We talk about the concept of record ID. So how do you construct a record ID? Record ID composed of page ID. So this page has a page ID value. Each page has a unique identifier, right? So record ID must have page ID value, which tells you which page hosts this particular record. But that itself is not enough, but because it only tells you you can find this record from this particular page. But it doesn't tell you where on this page this record locates at. Does that make sense? Of course, you can argue, maybe I don't need that, because once I know which page holds this record, I can fetch the page and linear scan to find the record. Of course, you can do that. But that basically means every time you try to find the record, you need to pay at least the cost of scanning 4 kilobytes of data. Suppose page size is 4 kilobytes. Does it make sense? Yes or no? So typically, in addition to page ID, I also store something called offset value. In that page, offset meaning the relative location of your record to either the starting or the end address of your page. So if I use starting address, the offset of this is 0. Let's say this is 10 bytes, and the offset of record 2 is 10. That tells you the starting address of that record on that particular page. Does it make sense? So record ID in a high level, of course there are many more details, right, than this. In fact, typically they don't use offset. They use something else to abstract away this offset, because offset is a bad choice, because if you move record on this page, the offset value may change. Does that make sense? Which implies your record ID may change for the same record, which is not good news. So typically what people do is at the end of the page, they store an entry, an array to store the offset value. So record ID 1 goes here, the offset of record ID 1 goes here, the offset of record 2 goes here, the offset of record 3 goes here. So the offset value may change, but the array index stays the same. So instead of storing the offset, I store the array index. On this page, I store the offset of that record. Now this is fixed. You can change the offset values, but the array index for that particular record stays the same. So the record ID stays the same no matter where you move this record into on that particular page. Does that make sense? So all I require you to know from this class is that record ID consists of two parts. One is page ID. The other is another object that tells you the location of that record on that page. And the other thing you need to keep in mind is record ID for a record typically is fixed in a database system. So far so good? Okay. And the rest you don't have to understand. So you can safely skip the slides for the other discussions. Okay? Now let's talk about indexing structures. If I have connections. You cannot always well. So before I talk about the next topic, which is indexing, I will run a simple experiment to show you the importance of indexing, right? To motivate the discussion. If I have network. Okay, so I'm gonna show you a simple experiment. So I'm gonna use our class database.
I think it's 5530.
Okay. DB.
Yeah.
So there are two tables we never use in our class, which is test 1 and test 2. So I'm going to show you what those tables are. So this is the schema of table 1, test 1. So it has 3 attributes: ID, name, and ratings. So ID is kind of like a primary key value. Name is I generate some random string simulating that's the name of a person. And rating is the rating value I give for that particular person. Does that make sense? And rating, I believe, is in the range of 1 to 100. So the value is 1 to 100. And the size of this table is about 5 million records. So I have 5 million records in this table. Does that make sense? What's interesting is if you look at on the ID attribute, I have on the rating attribute, I have a B tree index, B plus tree index. That's what I'm gonna talk about next. Imagine, this is just kind of some indexing structure built over that particular attribute. You may ask me, what's an indexing structure? Well, indexing structure is a data structure that enables you to do fast queries over that attribute. In high level, that's what it is. And I will talk about that in details next, after running our experiments. Now, I'm going to show you table 2 as well. It's exactly the same setup, ID, name, rating, and in fact, they have the same set of records. 5 million records. Only difference is, yes?
Certainly you could dim the lights.
Okay.
This would be a little hard to see.
The only difference is, it does not have that indexing structure on the rating attribute. That's the only difference between the two tables. That make sense? Yes or no? Yep. So what I'm going to do, I'm going to do a simple experiment. Okay? So I want to count how many people have a rating between 90 and 96. So if my rating is 1 to 100, and when I generate this table, I use uniform distribution. So that's about 5% of your data. Does that make sense? 5% of your data, because it's uniform distribution on ratings. So what's the count should be? It's 5% times 5 million, right? You can do that math, right? So let's look at how this query will run. So it's doing the counting, right? Does that make sense? So we'll take a little bit while because it's 5 million records, right? Hopefully it will finish. Now, first of all, you notice one thing, which is efficiency is a concern, right? When you talk about real database, rather than toy database you guys are building. When you have 5 million records, you do have to pay a time to answer your queries. In your product, you can probably run any queries as you wish because your table is so small. Any query will just finish in seconds, right? Here, a simple counting query may take this long, right? Okay, we got the result back. Remember this value here, 55 seconds, and that's about 250,000 records. Roughly about 5% times 5 million, that's the math checkout. Of course, there's some boundary values because it's uniform distribution, right? So it's not exact 250,000, but close. What I'm gonna do next is I'm gonna run exactly the same experiment on test 1. Does that make sense? Hope this works. Okay, I'm gonna run this. Do you see the difference?
Yeah.
Wow. So I was like a little bit nervous because I didn't run this for a few months. I hope the indexing structure is still there. But I hope I convinced you there's something here. If you are Amazon or Google or even Microsoft, you probably care about the difference, right? I mean, I should speak about that. Sorry, I have many friends in Microsoft. So, let me rephrase. If you are Amazon, Google, or Microsoft, even if you are Utah state government, you probably care about this, right? Does that make sense? Yes or no? I mean, I hope you care. Right? I mean, if you tell me you don't care, yes, nothing I can do. Right? I mean, it's like Utah state government tells, I don't care. Tax dollars, let's run it. 5 hours, 10 hours, don't care. But I hope they do care, right? So you see a difference, right? Exactly same table, no tricks, same thing, same setup. Does that make sense? And if you work for Google, let me tell you that if you joined Google or Microsoft 20 years ago, supposedly they were there, and back then database technology was like not as advanced as today. If you took our class today and go back 20 years and join Google and Microsoft, by doing this, you are set for life. Seriously, no kidding. You introduce this technology, you are done for your life. You can have fun. Essentially. Nowadays, of course, you cannot do this anymore because people know how to do this stuff. But 20 years ago, if you can do this, huge difference, right? Okay. So what I'm going to tell you next, of course, again, this is keep in mind this is undergraduate class. I cannot explain to you all the detail behind this magic, but at least I want to give you a feeling of this magic, how this magic is done. Okay? Does that make sense? Okay, now let's come back. And this is, keep in mind, this is a simple range query with aggregation. And you see a huge difference between the two already. What about joined over multiple tables? That's even more expensive, which means even more potential difference between the two queries, with or without index. Does that make sense? Right? So those are things I will try to get some idea across to you. Okay. Now let's come back here. And download the slides, and then we go from there. Of course, one more thing I want to show you before I go, since we're there anyway. What I'm going to do, I'm going to run this same query again. What do you expect on test 2?
It will be
It will be faster. Why?
Caps.
Let's see whether that's the case. Now it's faster. Why? Because the buffer manager. Because the buffer manager. Okay? Because of what we just discussed. But you may argue then, what's the difference between running test 2 and test 1 now with and without index? The point is, you cannot assume you have the buffer for yourself all the time. Chances are, by the time you run your queries, again, buffers are replaced with some other. Imagine, if this is the algorithm, by the time we talk about all the talking I did, probably millions of queries have been executed. Chances are your buffer is gone, long gone. Forget about it. Right? So you will still pay, maybe not 50 seconds, like 30 seconds. So indexing is still critical. And if I run test 1 again, my query will be faster too, because of the buffer. Yeah?
Actually, never mind. I'll ask you after class.
Okay, sure. Yes. Okay, so let me give you a quick overview of why this is the case and what happened behind you know, behind the scene, right? So review, we can skip this. I think I'll talk about this as well. So alternative file structure. So we talk about heap files. Another trivial alternative to a heap file is what we call a sorted file. A sorted file is nothing else but the exactly same thing as heap files, but records in a sorted file are sorted on some attribute. For example, I may have a student table that goes to a heap file unsorted. I can have the same student table goes to a sorted file where student records on that file are sorted based on their name. And this will make a huge difference in terms of fetching records from that file. And we will see that later on. I will have a discussion on that. And then later on, I will talk about cluster file with index and unclustered file with index if I have time today. So I will establish a cost model for our discussion, and these are the numbers that you need to keep in mind. I use B to denote the number of data blocks in your file, right? So how many pages in total you have in your file? Actually, I want to change this. I don't like this B notation. I will change this afterward. Later I will use n because I typically use n as the as the total number of data pages you have in the file. For now, let's use B because that's what's on the slide. That's actually I took that from the textbook. They use B, but I don't like B. B typically in computer science and in database particular, B typically denotes the size of a particular page. Rather than the total number of pages you have in your file. But for now, let's use B for that purpose. R is number of records per block, meaning how many records you have in a particular page. By the way, block and page are the same concept. Okay, Matt, can you turn on the light? So block and page are interchangeable. Okay. So a block is a page is a block. And D is average time to read and write this block. Of course, this is a really, really rough estimation because the time you take to read and write a block really depends on whether it's a sequential I/O or random I/O. The value of D may be hugely different between a sequential and random I/O. But for simplicity, I do not differentiate that in my cost model. I do not differentiate sequential and random I/Os in my cost model. And for the most part, I will do an average case analysis. But when needed, I will also ask you to think about the best case and the worst case scenarios. But for the most part, let's assume an average case analysis. What do I mean by average case analysis? Think about the rotation delay thing we talked about. The best case is the head of the arm is right on top of the page you're trying to read. The worst case is the head of the arm is just behind the page you try to read. So you have to wait for one full rotation for that page to come back. So the average is what? What we use? We use average, half rotation time as average rotation delay. That's kind of like an average case analysis. Does that make sense? So we will do that for the subsequent analysis too. So we make some assumptions in analysis. For heap file, we assume insertion happened in the end of the file. And for sorted file, in fact, let's ignore these assumptions for now because I'm gonna skip the dynamic update part. We just don't have time for that. So we will only talk about, we already have a heap file, we already have a sorted file. We only talk about the query cost, meaning fetching data or fetching record format. I will skip the discussion on deletion and insertions. So this is where these assumptions come into play. Okay, but we can ignore that. I'm not going to talk about dynamic insertion deletion anyway. Okay? So we'll ignore that. So the goal is to fill up this table up to this row. You can ignore the insertion and deletion for now. Okay? You can ignore the insertion and deletion for now. Let's look at up to here. what's the cost of scanning all records, what's the cost of quality search, and what's the cost of rich search. So I'm going to start with the simple stuff, which is for the heap file, what's the cost of scanning all records? That should be an easy one. How many, there are two questions I want to ask you, right? One is, actually, only one question, right? How many IOs? IO means how many input and outputs. Suppose, of course, another assumption in our analysis is buffer is empty to begin with. We ignore the effect of buffer, right? In all the analysis here, we ignore the effect of buffering. We assume the buffer is empty. Or you can assume there's a very small buffer. The effect of buffer is negligible. So what's the cost of scanning all records from a heap file? If you have B pages in the heap file, what's the cost of scanning all records? Huh?
B times R.
Okay, so I heard some. One answer is B. You have B pages you need to scan, and you pay B time for each page, so roughly B times D. The other answer is you have B pages, and within each page you have R records, right? So total cost is something like BR. Then there may be some factor of B, right? So which is which? So let's look at this carefully. B is total number of pages you have. To scan all records, you need to fetch all those pages from these two main memory. So you need to do this many I/O. And for each I/O, you pay D times, so it's roughly B times D. But what's missing here, in addition to this, once you fetch a page, suppose it's your buffer, it's your disk, that linked list structure we talked about, right? And you fetch this one by one. Once the page is in the buffer, you still need to go through this to get all our records. Does that make sense? Yes or no? Which is not captured by this formula right here. So there should be some BR cost right here. B pages and R record for each. But the important thing to note is that this operation, the time cost for this is not 2 times D. D is the time to fetch a page. The cost of this is to really another level of abstraction, which is your cache. You need to fetch this page record by record into your cache in order to read those records. Does that make sense? And let's assume that cost is X time per record. The observation is X is much less than D, because everything is in main memory now versus traversing data from this to bringing data from this to main memory. Right? We had that argument last time. Of course, you can argue, but there is a factor of R. So what about Rx of D? I can tell you this is still much less than D, as you can tell actually from my experiment. Once things are in buffer, super fast. Does that make sense? Which means these two terms, this dominates the second term. So in our analysis, we focus on I/O cost. We focus on I/O cost. In other words, we will ignore that second term. Do you follow me? Do all of you follow me? So that's the cost of scanning all records from a heap file. What about the cost of scanning all records from a sorted file? Second column. What's the cost of scanning all records from a sorted file?
It's the same.
It's the same, right? Doesn't matter. You are scanning all records, right? Whether you are sorted or not makes no difference whatsoever. You have to look at every page once. Okay, what about equality search? Equality search meaning, for example, give me the student record name Feifei Li. I'm doing an equality search on the name Feifei. What's the cost of that? For heap file and sorted file. Now, I make one assumption here, which is there is only one matching record for the value you are searching for. Because in the extreme case, maybe all records in the database have the value you are searching for, then equality search degenerates to scanning all records. There is no difference, right? So here I assume there's only one record with the matching value you are searching for. So what's the equality search cost for heap file and sorted file?
I'd say it's half of the first one, because I know that record could be the first.
Yes. So for the heap file, in the worst case, the record you're looking for could be in the last page of your file, and you have no way of knowing that ahead of time. So the only way you can find out is to linear scan through all the pages, and until the last page you find your record. Does that make sense? But since you mentioned it, I can imagine a best case scenario as well, which is the record I'm looking for is in the first page in my heap file. So I'm really lucky. Once I start scanning, I find it. I pay 1 IO. So in the worst case, it's B IOs. The best case is 1 IO. What's the average case? In the middle. So the average case is this for heap file. Does that make sense? Yes. Okay. Now what about sorted file? Of course, here we assume that the value you are searching for is the attribute that sorted file used to sort the records. Otherwise, the sorted file for this particular operation is same as a heap file. It's not sorted. So it has to be sorted on the attributes you are searching for. Otherwise, it's as effectively as just a heap file. Does that make sense? So here we'll assume the student file is sorted on the name attribute. What is the cost? What is the cost for equality search? Yes.
I think it's going to be some like log.
Something like log.
Because if it's sort
Log of base what? Base 2, base 10, base 100, base 2,
Base 2,
or
yeah.
over what?
BD.
B. Can someone argue to me why?
Because you can use binary search.
Kind of like a binary search, essentially. You go to the page in the middle. You know you have B pages, so you load B over 2's page. And you look at, and remember, records are sorted in a page and across pages. You look at the first record and the last record in that page, you look at the name value and compare it against the value Feifei. If it's in between, then lucky, you're lucky. This value is in this page. But if it's not, what do you do? If Feifei is less than the first name, first record on the page, you only need to look at pages on the left-hand side. Otherwise, you only need to look at pages on the right-hand side. But in either case, you reduce the range of your possible search to half, which is only B over 2 pages you need to look at. Then you recurse. If it's the first half of your pages you need to look at, you look at B over 4's page. Then you recurse. After, in the worst case scenario, after this many lookup operations, reading this many pages, you guarantee to find your value in a particular page. So that's the cost. Does that make sense? What about range search? Range search refers to the following operation. Essentially the operation I did just now. The query condition is not a single value, but a range of values. Make sense? What about range search for heap file, and what about range search for sorted file? What about range search for heap file? That's an easier one to answer.
I guess it's going to be half BD plus the range elements, 1 IO per range.
Plus 1 per
Range elements.
page
Page.
with values in your range, right? That's something you're trying to say?
Yeah.
Okay? But how do you do this? That's the question. How do you find out those values in the range?
Scan the page.
Well, heap file is tricky. If you think about it, for range search, because you don't know how many values are going to be in the range, whether it's 10 or 20 or 100 records, you don't know until you finish searching, right? So what you have to do in a heap file scenario? Well, you load the first page, scan through every record. As soon as you find a record in the range, you output that. But can you terminate your search? You cannot. Because you don't know whether there will be more records in the range or not. So you have to look at the second page. You have to look at the third page. You can only be sure you have exhausted all records in the range when, what happened? When you have scanned through all the pages. So the best case, worst case, average case, no matter which case you talk about, is always unless somehow magically you know the number of records in this range, then you can stop as soon as you have found those many records. In fact, let's come back and visit this value here. The reason the average case is half BD is that I tell you there's only one matching record. If I don't tell you that, even for equality search, using a heap file, you have to go all the way to the end. That make sense? Because you don't know whether there will be more matching values or not until you have exhausted all records. The only scenario you can terminate early for equality search over heap file is what? And for range search as well is when you know how many records will be satisfying your query condition. For equality search, that means if you know you are searching over a key attribute, whether it's a primary key or candidate key, then you know for sure there's at most one matching value for the value you are searching for because it's a key attribute. Why at most one? Because there could be no record with that value you are searching for. In that case, you have to go all the way to the end to know the fact that there's no record with that matching value. But once you find a value, and you know this is a key attribute, whether it's a primary key or candidate key, you can safely stop. Because there only can be one value at most with the value you're searching for, if it's a primary key or candidate key. Does that make sense? Otherwise, you have to go all the way to the end. Now, what about sorted file? What's the cost here? For range search. Okay, obviously, you're still going to pay that log 2b to find the first record in the range that you are searching for. But after that, what do you do? Do you have to go all the way to the end of the sorted file? The observation is you don't. All you need to, again, assuming sorted file is sorted by the attributes you are searching for. Otherwise, this doesn't work. This is effectively the same as a heap file. Once you find that first record in your range, what can you do? You can do linear scan from that record onwards because records are sorted until the first time you see a record that's outside the value, the range value you are searching for. Then you can stop. Why? Because again, records are sorted. So if you are within my range, you have to be in this part. Once you outside this range, it's impossible to have any other records with a value from this range. If you do, then that contradicts with the fact that it's sorted on this attribute. So the big picture is, this is your file, and each of this is a page. And you do this log bn thing to find, the first record in the range. Let's say you are searching for like this. So this is the first record with the value 7. You may have another record with the value 7. If, suppose this is not a key, right? If this is a key, then you can only have one value with value 7. But in general, suppose that's not a key. So you continue scan here until some page later, you find the first record, last record that's 12, another record that's 12. But then you find a record that's like 15. 12, 12, 15. Then at this point, you can stop. Because if you have a value between 7 and 12, you have to be within this range. You cannot be outside this range. Assuming sorted, of course, by x. With x. That make sense? Okay? So we fill up this table already. Like I said, I'm not going to talk about insertion deletion, so you can safely ignore that. Class file is something I'm going to fill up later on, so we can look at that later on. Okay? Keep in mind, there is an important assumption here when I write formula like this. So don't memorize formula. You need to understand what's going on. First of all, it's average case analysis. Secondly, for equality search, I assume that there is only one matching record. If that's not the case, the formula will be different, as we discussed. So far, so good? Yes?
For range search on the heap file, shouldn't that be half the heap?
Sorry, say again?
The heap file for range search?
I just explained, you have to look at everything, because you don't know how many records are going to be in your range. So you have to go all the way to the end to be sure you have found all records in the range.
So the average case would
There's no average case. Average case, best case, worst case, all B can be. You have to go all the way to the end. Unless somebody magically tell you ahead of time how many matching records you have, then you may be able to determine it earlier, so as you find those many matching records in the range. Okay, the question is, for a story file, how many pages you need to scan to find all the records in the range? Well, that's determined by two things. One is how many records are in this range, and how many records a page can hold. Suppose you have 1,000 records in this range, and each page can hold 100 records. That translates to 10 IOs, 10 pages. You follow me? So that's why I write here number of matching pages. You can calculate that based on how many records in the range and the size of each page, how many records can hold. Okay, we don't have much time left, so I will quickly give you some discussion. I think we're almost there. Now let's talk about indexing. The whole point of indexing, now once we understand sort itself, is the following trick. Remember, if you use the sort itself, the cost is roughly half of, is related to this. Log 2 of B, right? B is total number of pages you have. How do you improve the efficiency of this? Well, you can do nothing about B. B is number of pages you have, number of data you have. You cannot tell your boss, oh, I have a brilliant idea to build an efficient database. Instead of storing 1 billion records, let's store only 10 records. That doesn't go anywhere, right? Obviously. Right? So you cannot do that. So the only other factor you can control is the base. Can we go from here to, let's say, log 100 of B? You may wonder, what's the big difference? It's constant, 2 and 100. Now, let's do the math. This is same as log B over log 2, right? And this is same as log B over log 100. Yeah? Yes or no? This is a basic thing for any log operation, right? Let's use log 2 in all these calculations. So here I get log 2b back, not surprising. Log 202 is 1. Here I get log 2b over log 2 of 100, which is 2 to the power of 6 something, right? Because 2 to the power of 6 is 64. 2 to the power of 7 is 128. So it's 6 point something. Yes or no?
Yep.
So if you compare this value and this value, what's the difference? Let's say this is 6.5. You got about 7 times speed up by manipulating this space. Yes or no? Right? So I convince you, right? It matters. 7 times speed up. You may argue this doesn't matter, but if you drive here from Salt Lake to Las Vegas, 6 hours. So on the left, you take 6 hours. If I'm on my right-hand side, I got 6 times speed up. I will be there in an hour. So by the time you arrive in Las Vegas, I may become a millionaire or I may be broke already. So it depends on how my life goes. So there is a huge difference. 6 hours you can do a lot of things. So what I'm gonna show you next is quickly but But the question now remains is, how do you go from here to here? How do you go from here to here? You follow me? Okay. So for that purpose, I'm going to introduce the concept of indexes. So for that, I'm going to skip all this. I'm going to give you a quick overview of index. Then I will come back to that if I have time. I think we are running out of time. So maybe we just don't have time to go over all the details. But at least I cover Solify and the intuition of this. I feel good about it. Now, I give you a quick overview of B plus 3 indexes. Okay? So B plus 3 indexes is kind of like, this is exactly the structure I used in my experiment earlier. Right? I convinced you there's a big difference. That's precisely the structure behind the scene of doing the magic. So on a high level, a B plus 3 index is almost the same as a binary tree indexing structure. You guys have learned binary tree, right? Have you learned binary trees?
Yeah.
So what's a binary tree? If you think about binary tree, it's pretty much like this. You have a value 100. And here maybe you have 75. I don't know, here you have 288. And so on and so forth. It goes all the way to the leaf level. So you have multiple levels here. So these are all the items in your data set at the leaf level, and they are sorted, and you pick the middle value. For every 2 values, you recursively do this, you build a binary tree. And the idea is this is less than 100, this is greater than 100, this is less than 75, and this is greater than 75, and so on and so forth. This is less than 288 and greater than 288. Okay, sometimes you can have less than here and greater than equal to on the right hand side, but that doesn't really matter. Does that make sense? And to find a particular value, for example, how do I find value 88? I look up this node. If it's less than 100, I go left. If it's bigger than 100, I go right. And I do that at each level. Then I can find my item. So instead of paying, if I have n items, instead of paying n time, I pay log n time, log base 2 n time to retrieve my item. So that's a quick overview of binary tree, right? So what is a B plus tree? Well, a B plus tree is exactly the same as a binary tree, except that instead of storing only one value on every node, you store multiple values in a node. How about that? And you can do this because in a B plus tree, every node, this is the node, every node is a page. Meaning every node is roughly 4 kilobytes or 8 kilobytes, depending on your page size. You can totally store multiple values in a page instead of a single value. And the format of a B plus tree node, this is a B plus tree node, and in particular, this is the index entry. It has a key value and a pointer. Key value and pointer. This is one entry, another entry, another entry. Ignore the first pointer for now. Each of this is same as your binary tree structure. So you can think about this as your key value k, and this is the pointer. Let me use another color. So this is your k, and this is your pointer. So a binary tree is pretty much like a B plus tree, but it only has one entry. This is called one entry. This value plus pointer form an entry. Does that make sense? And what about this pointer? This pointer is the same as the P0, the leftmost pointer. Because the first entry in a node effectively can have 2 pointers, to the right and to the left. But other than that, you think about converting from binary tree to B plus tree. All you do, if you look at up to here, this is the same as your binary tree so far. I hope I convinced you that. This is 100, greater than 100, less equal than 100. All you do is keep adding entries to it until what? Until you run out of page size. Until you run out of space on page. That's all. That's a B plus tree. Then you got a B plus tree. To give you an example. Okay? To give you an example. So in the root, I have one entry only, which is 17, and I have 2 pointers. The right pointer is part of your entry. The left pointer is that leftmost pointer as I explained. And then I have two pages below that, page 1 and page 2. And those 2 pages have more entries, more than 1 entry. In fact, each of them have 2 entries. So 5 and its pointer 13 and its pointer 27 and its pointer 30 and its pointer. And each of these pages will have their leftmost pointer as well. You follow me? And you may wonder how those pointers are implemented in a vClass tree. Now this goes back to the concept of page ID I mentioned earlier. Each of these pointers is actually not a pointer, but in fact, it's just a page ID value. It tells you which page to load from the level below. It's simply the page ID for the page in the level below. So the way you interpret this is that all the database entries with value less than or equal to 17 will be on the left-hand side, and all the value greater than 17 will be on the right-hand side. And the way you interpret this is all the values less than or equal to 27 will be on this side. All the value greater than 27, but less than or equal to 30 will be this pointer. And all the entries greater than 30 will be this pointer. So on and so forth. Yes?
At which point you will add on the first root?
Yes, and root. Yes.
You have only
Oh, you have a root pointer. This is the same as the page ID value for the header page. You store that root page ID in your metadata table so that database knows where to start traversing your indexing. So it's stored in a fixed location, which is in your metadata table. Does that make sense? And the only minor difference I need to clarify is at the bottom, this is what we call the leaf level. These are the leaf level pages. These are the leaf level pages. At the leaf level, you store this entry and pointers, but those pointers are no longer pointing to a page. Those pointers, these pointers, point to data records. So those are RIDs, record IDs, rather than page IDs. So it tells you not only the page, but also the offset of that record on that page. So what it tells you is the record with this p-value 39 is in this page and in that offset location. The record with attribute value 38 is in this page with that offset. Does that make sense? And you can build bpass tree for different attributes. Here you can think about this as we build a bpass tree on the age attribute. So these are age values. I think I will stop right here. There are more discussions I don't have time to get into, like hash indexing, analysis on the bpass tree, and the difference between clustered and unclustered indexes. So I will not test those in my midterm, in my final. And for that reason, let me finish and answer your question. I will revise my homework 5 because the last part will depend on some of these knowledges. So I will trim homework, the last part a little bit to reflect what we have covered. Okay? And then I will use 1 or 2 minutes to talk about the finals. Okay? So the final will be whatever we have covered until today. And essentially, whatever that's reflected in your homework 4 and homework 5. Of course, I will change homework 5 slightly, the last problem, to reflect what we have covered. And some things we didn't manage to cover, but that's okay. I think I covered most of the things I like to cover. And we have quiz 4 out. Obviously, I don't have another lecture to conduct quiz number 5. So what I will do is, after homework 5 is due, I will release quiz 5 and with solution attached to a separate page so that you can test yourself and check against yourself. I will release that on Friday. Homework 5 is due on Friday. Friday, we do not have a lecture. You may wonder, how do you submit your homework 5? As I mentioned, we do not accept electronic submissions because we just cannot print 140 electronic submissions. So what you do is you will go to the TA offices on Friday before 5 p.m., remember, and hand in your hard copies of homework 5 to one of the TAs. The TA offices where you should go to is clearly printed on homework 5. It's not the regular TA offices. It's their research offices. So pay attention to the office number. It's in the 4th level of MEV. So you will go and find them there, and any of the TAs, that's okay. You just turn in your homework file to any one of them. Okay. One final thing, final test. Final test will be after the midterm, meaning I will not test anything that's already tested in midterm in the final test. And final test is subject to the same open book policy as we did for the midterm. So it's open book, but with certain restrictions. You cannot bring your own notes. You cannot look at any website other than the course website, and so on and so forth. So same policy. With that, and one final reminder, if you haven't done your course evaluation yet, you should go ahead and do it. That gives me useful feedback, so I can improve the teaching in the future. Lastly, before I enjoy teaching this class, I'm really happy that all of you take this class with me, and it's a lot of work, I understand. But I hope at the end of the day you learn. That's the objective. Okay? I have one question from Natalie and one question from there. Natalie, do you still have a question? Oh, I answered you. Okay. Do you have a question over there? You raise your hand. No. Okay, with that, I see you in the final test. The time of the final test is available from the syllabus and from the course website as well. I will send out a reminder too. Yes.